Senior Training Lead and Evangelist with Oracle University. Let's take a look at some of the features and use cases of OCI container instances. Alright, it's time to get started. Let's discuss the first feature, which is the serverless experience. OCI container instances run your containers on serverless compute, which is optimized for container workloads. The underlying infrastructure is fully managed and hardened by OCI. You can focus on building your applications without having to worry about provisioning, patching, or managing any kind of servers. Simple pay-per-use pricing. You only pay for the CPU and memory resources allocated to your container instance at the same price as the regular compute instances for the chosen shape. There are no additional charges or tax for the seamless operations provided by the serverless platform. No costs are incurred when the container instance is not active. That is, a container instance will be inactive as soon as the containers within the instance stop and the auto restart policy is not enabled. Let's understand how simple, fast, and flexible are OCI container instances. Easy to run with flexible configuration. Running a new container instance with one or more containers only requires a few simple parameters via CLI, API, or the OCI console. You have the flexibility to specify your preferred shape such as E3 or E4 flex, CPU and memory resources required, and the networking configuration. You can also configure environment variables, startup options, resource limits, etc. for each container. This enables you to launch containers instantly, configured just the way you want them to support your needs. Maximum CPU and memory. You can allocate all the CPU and memory provided by the underlying compute shape to a container instance to run even the most demanding workloads. For example, you can allocate up to 64 cores, which is around 128 vCPU and 1024 GB of memory to a container instance with the E3 and E4 flex shapes. Open Container Initiative compliant. OCI container instances support pulling container images from Open Container Initiative compliant container registries. It also includes the OCI container registry. Talking about security, networking, and observability. Strong isolation. Container instances provide a dedicated environment with strong isolation to each container instance, same as virtual machines. Containers running on a container instance do not share OS kernel and CPU or memory resources with other container instances. This enhances your application's security posture without compromising on its performance. You can also set up OCI container registry with private access and enable the security scanning for your container images. Integrated networking and access control. Each container instance is connected to a subnet in your VCN, ensuring secure communication. You can optionally assign a public IP to a container instance if the container needs to be accessed publicly. The containers on the instance share the same networking namespace. They can find each other on the localhost or 127.0.0.1 IP address. Using OCI identity and access management, you can configure policies to control access to other OCI services or resources from the container instances. Logging and monitoring. Using the built-in logging, you can view your container logs in the OCI console or pull them using the API. OCI container instances also provides built-in metrics to monitor CPU and memory utilization, disk I/O, network receive transmit bytes, etc. Now let's cover some of the common use cases for OCI container instances. Container instances are useful for running containerized workloads without a container orchestration platform like Kubernetes. They are great for short-lived tasks such as build and deployment jobs, automation tasks, and data or media processing. With container instances, running a container is easy with an API call or a CLI command, making it ideal for DevOps, operations, and data processing workflows. Container instances can also run isolated web applications or RESTful APIs, allowing you to use your preferred framework for development. Applications can be packaged as container images and run individually or in a group. Containers on the same instance communicate over localhost or the loopback interface, allowing for full stack application deployments and sidecars. Container instances can assist with migrating legacy monolithic applications to the cloud, which are typically not designed for cloud-native platforms like Kubernetes. By containerizing these applications, you can run them on container instances without the operational burden of managing servers or virtual machines. Additionally, you can allocate the necessary CPU and memory resources to meet the demands of even the most resource-intensive applications. Container instances allow for quick creation and removal of development and test environments, replacing the need for local workstations or virtual machine management. This increases the productivity and reduces the resource limitations and potential risks. It's also useful for setting up test backends needed for application development and testing. To wrap up, in this lesson, we covered some of the key features and best use cases for OCI container instances. I hope you enjoyed the lesson. See you in the next one. Thanks for watching. Hello, I am Mahendra Mehra, Senior OCI Instructor with Oracle University. Welcome to our lesson on working with container instances in Oracle Cloud Infrastructure. In this lesson, we will explore the key concepts and features you need to know to effectively manage container instances. Let's jump right in. Before we dive into the details of container instances, let's first discuss IAM policies. IAM policies in OCI govern access to container instances and define permissions for different users or groups. These policies control who can create, modify, or delete container instances within your tenancy. As you can see, there are two different individual resource types that you can choose from. One is compute-container-instances. The other is compute-containers. These two individual resources can also be clubbed as aggregate resource type under the compute container family. There are different permissions associated to different level of access. For example, inspect level of access provides you only with inspect permission, whereas read allows you both inspect and read permissions. In the case of use level of access, you get inspect, read, update, start, stop, and restart permissions. Whereas with the manage level of access, you get the access to all the permissions that are listed out here. Also make a note for compute-container-instances, all permissions will have prefix compute_container_instance followed by the permission name. For example, the inspect permission here will be defined as compute_container_instance_inspect. Talking about the compute container individual resource type, here as you can see, the permissions are different as compared to the one we saw in the previous slide. You get inspect, read, update, log retrieve, create, and delete permissions based on different level of access such as inspect, read, use, and manage. Also make a note, all the permissions here has prefix compute_container, and for example, for inspect permission, it will be defined as compute_container_inspect. Understanding the policy syntax is essential for effectively managing access to container instances. Let's look at some of the examples. I'll be presenting some of the examples of policies that can be used when interacting with container instances. Depending on the use case, this resource type can be aggregate or individual. For example, if you want to let the users do everything using container instances which is launched within the cloud network and subnets in the compartment ABC, these are the list of IAM policies which you must have in place. You must allow your user group to manage compute container family in compartment ABC. The other permission is to allow group to use virtual network family in compartment ABC. The third permission is to allow your group to read repos in tenancy. Another example is if you wish to control the access to container instance using network security groups, the user group should be allowed to use network security groups in the given compartment. For example, here the statement defines we are allowing container instance launchers group to use network security group in compartment A, B, C. So basically, if you're planning to control traffic to and from your workloads within the container instances, you must have this particular policy in place that allows you to use network security groups within the compartment. Now, another example is if you want to allow container instances to pull images from container registries, private repositories, we will have to implement access policies at tenancy level, for which the first step is to establish a dynamic group for your container instances. And to do so, you'll have to use the following syntax. All in curly braces, you have to specify resource.type equals to compute container instance. And then you'll have to allow your dynamic group compute container instance dynamic group to read repos within the tenancy. So you'll have to write the following policy which allows the dynamic group we just created in step 1 to read repos within the tenancy. These actions will enable seamless image retrieval, streamlining the deployment process for containerized applications. Another use case would be to ensure the container instances have necessary permissions to access vault secrets for image authorization. In this case, we need to set up appropriate access policies. Well, firstly, you'll have to create a dynamic group encompassing all the container instances which are requiring read permission. So in this case, we have specified the rule as all resource.type and provided the name compute container instance. And the name of the dynamic group is container instance dynamic group. Next, we establish a policy granting the dynamic group read permission to the specific vault secrets. For instance, the policy statement allow dynamic group container instance dynamic group to read secret bundles in tenancy enables the group to access all vault secret bundles within the tenancy. Overall, if you want container instance to pull container image from your private repositories, you'll have to first store your credentials as secrets within OCI vault and then allow OCI container instances to read those secret bundles within the tenancy. It is important to note that these policies provide broad access by default. However, you can utilize standard IAM policy mechanisms to refine the permissions, such as restricting access to specific container instances or secrets within the compartment instead of tenancy. Let's take a look at container instances shape that are managed by OCI. In OCI, container instances offer various shapes, each designed to suit specific workload demands. You have the choice of CI standard E3 flex, CI standard E4 flex, and CI standard A1 flex shapes. One standout option is the flexible shape, granting you the freedom to adjust number of OCPUs and memory allocation when initializing your container instance. This adaptability empowers you to fine-tune performance and cost effectiveness by aligning the container instance precisely with your workload requirements. Each of these shapes features extended OCPUs, allowing you to create container instances with cores that surpass the standard limit. Additionally, the network bandwidth scales in correlation with the OCPUs, ranging from 1 Gbps per OCPU to a maximum of 40 Gbps. Every shape includes 15 GB of ephemeral storage and one virtual network interface card, also known as VNIC, for seamless integration into your infrastructure. Now let's understand what is this concept of extended OCPUs. Extended OCPU container instances are designed for demanding workloads that need more cores than the standard configurations. With extended OCPU container instances, user can exceed the regular core limit, accommodating high-performance applications that require additional processing power. You can create container instances with extended OCPUs to tailor resource allocation to the specific needs of your workload, ensuring optimal performance. However, it's important to note that due to the increased core count, container instances with extended OCPUs may take longer to create compared to instances with standard configurations. Well, let's discuss ephemeral storage. Ephemeral storage is shared storage allocated to a container instance and its containers. It plays a crucial role in various aspects, such as storing container images and supporting containers root overlay file system. Monitoring ephemeral storage usage is important for managing resources effectively. You can access this information through the OCI console, where you will find metrics related to ephemeral storage usage. And this is available within the container instance details page. Ephemeral storage capacity plays a critical role in supporting various resources within container instances. Let's explore the key components that consume ephemeral storage. Starting with container images. Firstly, container images utilize ephemeral storage to download, unpack, and prepare for deployment on a container instance. It is important to note that the amount of free space required can be up to twice the size of the container image. For example, with a default ephemeral storage capacity of 15 GB, container images should ideally be less than 7.5 GB to ensure successful deployment. If there's insufficient free space, the creation of a container instance may fail. Secondly, container logs are another consumer of ephemeral storage. Each container retains up to 20 MB of log files, contributing to the overall usage of ephemeral storage. Additionally, the container's root overlay file system relies on ephemeral storage for file backups, ensuring data integrity and reliability. Moreover, empty dir volumes can utilize ephemeral storage as backup storage, providing temporary storage solutions for container data. Finally, internal system processes within the container instance also utilize a small portion of ephemeral storage to support essential system operations. And we will continue exploring container instances in the next lesson. I hope you enjoyed this lesson so far. See you in the next one. Thank you for watching. Welcome back. Let's continue exploring container instances from where we left off in the previous lesson. Moving on to the container instance creation wizard, let's explore the creation basic details section. Under networking, you will configure the network details for the instance. This includes specifying virtual cloud network and subnet where the instance will be created. You have the flexibility to choose whether to use an existing VCN and subnet, create a VCN or subnet, or enter the OSID of an existing subnet. You also have the option to assign a public IPv4 address to the instance. This is useful if the subnet is public, as it allows the instance to be accessible from the internet. Additionally, you can access advanced options by clicking Show Advanced Options. Here, you can configure settings such as using network security groups to control traffic, specifying a private IPv4 address, assigning a DNS, and setting a hostname for DNS within the cloud network. Under the Advanced Options tab, you can specify the following settings. Firstly, the graceful shutdown timeout allows you to set the amount of time the container instances waits for the operating system to shut down before powering off. Next, you'll choose the container restart policy. You have three options to select from. If you select always, containers always restart, ensuring they remain running even after successful exits. This is useful for critical services like web servers. If you go for never, containers never restart, regardless of the reason for their exit. If you choose on failure, containers restart only if they exit with an error, ensuring that specific tasks complete successfully. You can also add tags to the container instance under the Tags tab. Tags provide metadata to help organize and manage your resources effectively. You can apply both free-form tags and define tags provided you have the necessary permissions. Let's now dive into configuring containers for your container instances. Firstly, you'll need to enter a name for the container. This name doesn't need to be unique as each container is uniquely identified by its OCID. However, it's advisable to avoid entering confidential information for security purposes. Next, under the image section, you'll select the container image for your container. You have multiple options for the image source. One of the options is to use OCI container registry, that is Oracle Managed Registry for storing, sharing, and managing container images. The other option you have is to choose external registry. It uses images from the third-party vendor such as Docker Hub. Here you must specify the registry hostname, the name of your repository, tags if any, and based on if it's a public or a private registry, you can go for none, basic, or OCI vault secret credentials type. Like I said, the vault secrets for image pull authorization securely manages credentials for private registries or repositories using OCI vault service. In your use case, if you're pulling images from a private repository and if you want your credentials to be stored securely, in that case, you can use the vault secrets for image pull authorization. Additionally, you can set environmental variables for the container under the environmental variables section. These variables customize the container's execution, allowing for greater flexibility. For example, you can specify variables like nginx_port to customize your nginx behavior or mysql_password to customize your MySQL containers behavior. Let's continue configuring containers for your container instance. On the Resource tab, you have the option to fine-tune the amount of resources allocated to the containers. You can specify resource limits in absolute or percentages, providing flexibility in resource management. Remember, by default, the container can utilize all available resources in the container instance. If you want to restrict the amount of resources that the containers consume, be it your vCPUs or memory, you must choose the Enable Resource Throttling option and then provide an absolute or percentage value to split resources amongst the containers. Moving on to the Startup Options tab. Here you can configure additional settings such as working directory, command, and command arguments. These settings allow you to customize the startup behavior of your containers, ensuring it behaves as expected upon initialization. Lastly, on the Security tab, you can specify security settings for the container. Let's take a closer look at the Security tab and the various options available. Firstly, you have the option to enable read-only root file system, which restricts the write access to the root file system of the container. This enhances security by preventing unauthorized modifications to critical system files. Next, you can select the Run as non-root user option to ensure that the container does not run with root privileges. When enabled, the container runs with a specified user ID and group ID, enhancing security by minimizing the potential impact of security vulnerabilities. It is important to note that when using Run as non-root user, the user ID cannot be set to 0, which is for the root user. You can set the values for user ID and group ID anywhere between 1 to 65535 if Run as non-root user is enabled. You can also configure Linux capabilities for your container under Configure Linux Capabilities. Here you have the flexibility to add or drop specific Linux capabilities as needed. By default, the container launches with several capabilities, which you can choose to drop to further enhance security. Now, before we move ahead, let's take a look at some of the important points which are good to know when working with container instances. First thing is setup of IAM policies. Appropriate IAM policies should be assigned to user groups which are dealing with container instances. When creating a container instance, make a note you can create a maximum of 60 containers on each container instance. When it comes to managing container instances, you can start, stop, and restart a container instance. Container instances use standard shapes which pause billing when a container instance stops. Talking about metrics, you can monitor the health, capacity, and performance of your OCI container instances by using various metrics which are available under the Container Instance Details page. A point to note when deleting a container instance is when the containers are deleted by the service, any data on the ephemeral storage is lost. To wrap up, in this two-part series of working with container instances, we covered the IAM policies and other configuration settings necessary